In this video, we're going to summarize some of the important features about vectors that we saw in the previous preliminary examples. All right, so here we're going to talk about vectors in both 2 dimensions and 3 dimensions. So let's let the vectors a1i plus a2j, and that's going to be a vector in 2 dimensions because we have 2 components, I and j, and b1i plus b2j plus b3k, this is a vector in 3 dimensions, b vectors. Okay, so we have the length of a1i plus a2j is just that magnitude using the double absolute values, which is equal to the square root of those components a1 squared plus a2 squared. So we saw that above. And so we also have a notion, or kind of in the same way, we can consider the length of a vector in 3 dimensions. And it's going to be a very similar formula. And you could think about why that is. It's going to, again, use that Pythagorean theorem. And so the magnitude of such a vector is going to be the square root of the squares of the components. Okay. Our next takeaway here are if we consider, or is considering if 2 vectors are parallel. So it turns out 2 vectors, u and v, are parallel if one is just a scalar multiple of the other. So we can write, say, u as some scalar lambda times v. And we saw this in our preliminary example. So notice in the case when we multiplied our vector v by 2, we got a vector that was in the same direction over 2 up 3 essentially as v. It was just longer, but these 2 objects, v and 2v, are parallel. So we can really see that graphically in that example. And now the final concept we have here is that of a unit vector. So a unit vector is a vector of length 1. So that might not be too surprising. We see unit functions or unit fractions rather, are fractions in which the numerator is 1. So a unit vector is a vector in which its length is 1. And what's really cool is that given any non-zero vector p, we can make it into a unit vector by taking p and dividing by the magnitude of p. So the claim here is that the vector p over magnitude of p is a unit vector that points in the same direction as p, meaning it's parallel to p. So let's write that down, i.e. p vector over the magnitude of p is parallel to p. And we can see that, so the magnitude is just a constant. So essentially what we're doing here is multiplying our vector by 1 over a constant, which is also a constant. Okay, but let's just finish this off by looking at an example to convince ourselves that by dividing by the length of a vector, we are in fact making a vector that is of unit length or length 1. All right, so we can just write down here our example. So let's consider the vector p to be the vector 3i minus 4j. Okay, so now let's compute the vector p divided by the length of p. So what would that look like? Well, again, p is just 3i minus 4j. And then the length or magnitude of p would then be the square root of 3 squared plus negative 4 squared, which is 3i minus 4j over the square root of 3 squared is 9, 4 squared of 6 is 16, so 3 plus 9 is 25. So the square root of 25, which is just 5. So this would become 3 over 5i minus 4 over 5j. So now this vector that we just got, we are claiming has length 1, meaning it's a unit vector, and it's parallel to p. So being length 1, it's a unit vector. So we can see that this vector should be parallel to p. And why is that? Well, all that we did was we took p and divided each component by a scalar of 1/5. Okay, so yes, it's parallel to p. So I'd like you to check that this vector does indeed have length 1. You might be able to convince yourself of it right away, but I encourage you to go through the algebra and the steps just to show it so you can justify to yourself and you can really see concretely why this vector does indeed have length 1. And so in general, that's our approach. If we want to create a unit vector that's parallel to our given vector, is we divide by that vector's norm. Awesome. All right, thanks for watching, everyone. You're now ready to tackle the examples and exercises in these sections. Thanks for your work.